This is a tutorial on the one-way analysis of variance. It's a procedure when there is one independent variable with two or more levels and one dependent variable measured on an interval or ratio scale. I'm going to cover levels of measurement and how the analysis of variance uses the dependent and independent variable, the role of the research question and hypotheses, and then I'm going to go into the anatomy of an analysis of variance problem. I'll cover the within subjects and between subjects variance, how to interpret it, and also how to approach an evaluation. There are four levels of measurement. The foundational research was done by S.S. Stevens. There are, at the lowest level, would be nominal, and examples of those are like colors of things, ethnicity, gender, ID numbers, things that you count, and so forth. Ordinal means that the data are ordered in some particular way, such that higher numbers are reflective of a higher rank. Examples might include things like attitude scales or satisfaction scales, from dissatisfied to satisfied, or strongly dissatisfied to strongly satisfied. The other two levels of measurement are ratio and interval. We use these interchangeably. These are defined by continuous type of data. The only difference between interval and ratio is that ratio data have a true 0 point. The independent variable in an analysis of variance must be categorical or nominal. The groups have to be independent of each other in an independent one-way analysis of variance. We're not going to go into the dependent version of the one-way ANOVA, but that is possible. The dependent variable must be on a ratio or interval scale, and you must be able to use valid and reliable measures. The research question drives the entire research project. Research questions are typically 30,000 foot views of the design mechanics, and they establish the relationships between two or more variables. The characteristics of the independent and the dependent variable are defined in the research question. So you would probably want to phrase the research question such as, to what extent is the independent variable related to the dependent variable? Now this sounds like correlation, but actually it's at a very high level, and we're not talking about a statistical test. We are identifying the characteristics of the independent and dependent variable and their functional relationship. Research questions inform the hypotheses which follow. So research questions are not identical to hypotheses. Hypotheses are written in such a way to be tested. There are two types of hypotheses that we will use, and it will be important for you to state the null and the alternative or research hypothesis in every homework problem that involves a statistical analysis. You can write the null hypothesis in the following way. There will be no difference between group A, whatever that is, and group B, whatever that is, on the dependent variable as measured by whatever instrument that you're using to measure it. If you have more than two groups, then you would phrase this as follows. There will be no difference among groups A, B, and C on the dependent variable as measured by the instrument, whatever that is. There are two forms of the alternate or research hypothesis, the non-directional type and the directional type. Throughout this course, unless otherwise specified, alpha will be at the 0.05 level. In a non-directional hypothesis, you're only asking the question if the two means are different. You're not asking a question that would imply that one of the means will be greater or less than the other. When you do this, you have to split the 0.05 into two ends of the distribution such that there is 0.025 on one end and 0.025 on the other end. So let's take a score on something, and let's say that we computed a mean, and we were asking the question, is one group different from another group? And let's say that the mean of one group was 77 and the mean of the other group was 74. Well, in a non-directional hypothesis, you can see from the diagram here that 77 is inside of the normal distribution that's not shaded. So anything that is inside the normal distribution that is not shaded, that is, it's in between the positive and negative critical values, then those are values that we would not consider significant. They would be typical of that distribution. But if we cast this as a directional hypothesis, then you can see that 77 falls within the shaded area because we put all of the 5% of the curve onto one end of the distribution. Now this works out great provided that the direction of the difference is in the intended direction. You would never write a directional hypothesis unless there was evidence to support that a direction was reported in the literature. So in the case of the directional hypothesis, you can see that we put all the significance area, the 0.05 or the 5% of the area under the curve, to one end of the distribution. And in this case, 77 is a significant value. It's significantly different from 74. I'd like to talk just briefly about why random sampling is important, and it really is the piece of statistics that holds everything together and allows us to draw a sample from a population, perform a statistical test, and then infer the results back to the population. So in order for that to happen, you first must develop a sampling method such that every person or every element in the population has an equal probability for being part of the sample. So let's say, for instance, that there were 1 million people in this population, and we determined we needed a sample size of 80. So we would use a simple random sampling process, and we would draw a random sample from the population, perform the statistical test, and if the results were such that the observed p-value, the probability value, was less than 0.05, then we can infer those results back to the population. If our p-value was equal to or greater than 0.05, then we would retain the null hypothesis and say that there is no difference in the population. So let's take a quick look at the anatomy of a results for a one-way analysis of variance. You can see in the inverted pyramid where I have general at the top and specific at the bottom, and it kind of follows a funnel, and that's exactly the way that you need to organize your write-up. Begin with the general statements. Of course, this is after you have provided the background and you're going to state that you're going to test hypotheses at the 0.05 level. Then you're going to report the descriptive statistics. You can make observations. Anything that you put in a table must be interpreted in the text that follows it. So never leave a table with numeric information in it and not have a conversation, not discuss, not interpret what that means. In a one-way ANOVA, you can say things like, it appears that the means are different, but in order to determine if they are statistically different, then an analysis of variance was performed. So then you would move into reporting the inferential statistics, and you would begin by providing a table on the analysis of variance, and probably followed up by a post hoc test if the ANOVA was statistically significant. Following the table is going to be your interpretation of the results. So you're going to test everything at the 0.05 alpha level. The analysis of variance uses an F-test, and you're going to use the p-value to make your decision. I want to call your attention to the information I've placed in the upper right corner of this screen, and it has a yellow background. If you would make a copy of this, put it on a sticky note, and then stick that note onto your computer monitor. Every time that you do a statistical test, refer to this. I promise you it will work every time. You may need to adjust if it is a directional hypothesis, then you'll need to adjust the wording accordingly. So when you go to interpret, you're going to compare the observed p-value that you'll find in your ANOVA table, and you're going to make a decision on that based on the relative position of the p-value versus alpha. So if the p-value is less than alpha, then you can conclude, or actually you would first reject the null hypothesis, and then you would conclude that there is a significant difference. Now what you're going to need to do following that is to couch your conclusion within the appropriate context of the problem. Rather than just calling these numbers, you would probably want to refer to them as a particular group's sample mean, and that is measured by whatever instrument they're using to measure it. After you have written your conclusions, then you're also going to want to complete an evaluation of the statistical outcomes. One of the things that you can do is to discuss the limitation on inferences to the general population. For example, was random sampling used? Was this an experimental study that had random assignment? Was the sample size small? Was the method something other than experimental? I have random assignment there twice. We can eliminate that. And then was there a presence of a control group? So when you have random sampling and random assignment, and you have an adequate sample size, and you followed a experimental methodology, and you have a control group, then those are very strong positions supporting your inference to the population. But if you didn't use random sampling, and there was no random assignment, and the sample size was small, and you may or may not have had a control group, then these are limitations on the inferences to what you can make to the general population. Let's take a look at testing the assumptions. You'll need to test the assumptions for every problem that you work in this course, most importantly in the assignments, and then of course on your final project. So we'll begin with just the raw data, and that's what you see in the upper left corner. It's just a table of all the raw data, and I just made these data up. They're random. I did try to cast the data such that there would be a significant difference, and then we could talk about what that looks like on the F-test and then how we interpret that uh, using the post hoc test. So the first thing that you would want to do is to look at the numerical characteristics of the distribution. So here we see the mean, median, and mode. In a theoretically normal distribution, the mean, median, and mode lie on top of each other, so there's no differences. And you can see that for group A, for group B, maybe for group D somewhat, that the mean, median, and mode are fairly close, but in group C you can see that there is a difference between the mean, median, and mode in that distribution. Then let's go over to the next test, and this is the Shapiro-Wilks test of distributional symmetry, and you're going to want to look at these p-values, and you're going to test these against 0.05. So all of these are greater than 0.05, and therefore you can conclude that these data appear to be normally distributed. You may want to keep an eye on group C, because that's fairly close to 0.05, and then when you go over and look at the histogram, you can see that it doesn't really look normally distributed. Then go and compute your QQ plots, and again, if you look at group C, you have this kind of a zigzag pattern. Whereas the other groups, all of the data tend to be fairly close to that normal distribution line. This is not a scatter plot that you would do in a correlation, so we're not talking about linear relationships or anything like that. Basically, what we're trying to observe here are the relative distances of each of these points to the normal curve line, and is there about as many above the line as there are points below the line, and those are some good indicators that the distribution is normally distributed. And then finally, after we wrap up our test of normality, we go down to Levin statistic. And here we see, now Levin statistic is used to test the hypothesis that the variances among these four groups are equivalent. And because the p-value associated with Levin statistic is much greater than 0.05, then we can conclude that the variances are equivalent. And if you go up here again to look at the raw data where I've computed the standard deviations, they're all fairly close, so that doesn't really come as a surprise to us. There are two kinds of variances that are calculated in an analysis of variance. The first is called the within subjects variance, and what we do here is to compute the variance within each of these groups, and the analysis of variance calculator will do that for us, and so that's the within subjects variance is 289.68. We're also, at least StatCrunch is going to calculate the total variance, and the way that you do that is to compute the grand mean, that is taking all, I believe there are 10 data points per group, so you have 40 pieces of data. Compute a mean of that, and then you would go through and compute the sum of squares. You subtract the mean from each of those values and then square that difference and then sum across all 40 of those calculations, and that would be the total variance. So that would give us the total variance and the total within subjects variance. So finally, we're left with the between subjects variance. And for that, we're just taking these four means here, and we're computing a measure of the variability across or among these four means. So again, we would compute a mean of those four means, which would be identical to the grand mean that we would have computed up here for the total variance, and then perform the sum of squares calculation, and that comes to 83.10. I often see students will put in their write-up that F is really close to 1. Don't do that, because closeness only counts in horseshoes. In statistics, you have to use a p-value, and the p-value is telling you whether the F ratio is close to 1 or is it significantly greater than 1. And so you can see here that the F statistic in this analysis of variance is 41.83. Well, just by looking at it, we would probably say, yes, that's a fairly large number, and it looks much larger than 1 to me. But don't make those kinds of observations to hang your decision. Rather look at the p-value. And since this p-value is less than 0.05, then we can conclude that in this analysis of variance, this one-way ANOVA, at least one pair of those means are significantly different. Let's move to the post hoc test. So we determined that the F ratio was significant, and that only told us that at least one pair of those means are different. In a post hoc, we want to compute how many combinations. So there are two parts of probability that you've probably heard of. Those are called combinations and permutations. Combinations, the order doesn't matter. So what I mean here is if we subtract A from B, it's the same as subtracting B from A. So the order doesn't matter. In permutations, A and B and B and A are different from each other. So order does matter, but in post hoc tests, we're only concerned with combinations of things, not permutations of things. So we know that if we plug in the values of n factorial, that's n things taken 2 at a time, then you follow those calculations through and it will equal 6. And then you can confirm that by actually writing out all of the different combinations. So there's A against B, A against C, A against D, B against C, B against D, and then C against D. 6 pairwise combinations. Now then, here are the results of the post hoc test. And what you can see here is that A is different from B, C, and D. We know that because we look at these p-values. And we go down to B. So B and C are different because of that p-value. And B and D are different because of that p-value. The only pair that is not significantly different is C compared to D. And we know it's not significantly different because this value of 0.46 is greater than 0.05. So now what I've done is to plot these means using the means plot. And here you can see the mean for A, and then this is, I think, 2 standard deviations on either side of the mean. And then the mean for B and that bandwidth, C and D. Because the confidence intervals of C and D overlap, we know that they are not different from one another because a value here in C is a likely value in D. So if I said that the mean was 3.5, you could not tell whether that mean came from group C or group D. However, with A and B, you can see that A is different from B because those confidence intervals don't overlap, and A is different from C and D because those confidence intervals don't overlap. And then all the other combinations that I referred to earlier in discussing the results of the post hoc test. So finally, you're ready to write your evaluation. And the one thing you want to begin with is to summarize your test of assumptions. And all of the groups appeared to be normally distributed. You may want to call out that group C was unusual. We can claim that all the variances among the four treatment groups were equivalent. There was a fairly small sample size, so if it would be unlikely that 10 would have been enough. I think usually you'd probably want at a minimum 20, more like 25 or 30 per group. We'll learn more about computing a power analysis and estimating a sample size later in the course. And then finally, are the results practically significant? So you can have two means that are statistically different, but they're not practically different. So, for example, let's say we took two groups of children, and one group had an IQ or a standard score, let's say a standard score on a national test of 500, and the other group had an average score on this national test of 550. And we detected that one group was significantly different from the other. However, if you look at the whole range of scores from, say, 0 to 1,000, then that's 50 points is a very small difference. And I don't know that you would develop any kind of interventions based on such a small difference. So things can be significantly or statistically significantly different, but they may not be practically different unless the effect sizes are large, that is, the distance between means are relatively large, or that if you're doing a correlation, that the R squared value might be greater than 0.75 or 75%. So what have we done here? We've kind of gone through the components of a one-way ANOVA. We talked about levels of measurement. The independent variable needs to be measured on a categorical or ordinal ratio, whereas the dependent variable needs to be measured on a interval or ratio level of measurement. We talked about the developing or stating a research question. It's usually in terms of how variables are functionally related. And then we went through the process of developing a hypothesis, and we talked about the null hypothesis and how to state it. We talked about directional and non-directional types of hypotheses for the alternate or research hypothesis. We talked about random sampling and why that is so important in order to draw an inference back to the population. I went over the anatomy of your write-up for a one-way analysis of variance. Be sure that you refer to all of the resource documents in Module 6 and Assignment 6.3, and that you read the rubric carefully. I went through testing the assumptions for normality and equal variance. I deconstructed the two variance components, the within subjects variance, often called the error variance, and then the between subjects variance, often called the treatment variance. And then we looked at the ANOVA table, the post hoc analysis, and how to interpret that. We went through the means plot and interpreted that, and then ended with how you would write up your evaluation. That concludes this presentation.